You've already seen how to solve a first-order linear differential equation. In this video, we outline how this class of differential equations can be used to model biological processes. Specifically, we'll focus on pharmacokinetics and build a couple of simple models that describe the fate of drugs in the body. Here's our first scenario. Suppose a drug is administered orally to a patient. Suppose also that the patient metabolizes the drug at a rate of p times 100% per hour. Assuming the drug is administered at one and only one point in time, how long will it take for the amount of drug in the patient's system to fall below 1% of the original dose? Let's use a differential equation to model this problem. Let U of t be the amount of drug, say in milligrams, in the patient's system at time t measured in hours. The concentration of the drug in the patient's system is diminished over time because it's metabolized. We'll assume that the rate of metabolism can be modeled as a first-order kinetic process. In other words, we'll assume that the rate of metabolism is proportional to the concentration of the drug itself. We'll also assume that the drug is dissolved in a constant, well-mixed volume. This is important, at least in part, because it allows us to discuss the amount of drug interchangeably with its concentration. With our assumptions in place, we can state the following recursive model for the amount of drug in the patient's system. Here, K is a positive constant connected to the metabolic rate. Larger K means the drug is metabolized more quickly. The negative sign is there to remind us that metabolism contributes to a loss of the drug in the patient's system over time. We also attach an initial condition to our differential equation model. We take time 0 to be the exact moment when the drug was administered. So U at time 0 is equal to the amount of the original dose, denoted here as U0. What we have is a recursive model stated as an initial value problem. The initial value problem involves a first-order linear differential equation, exactly the kind of equation we know how to solve. To apply our standard procedure, we write the differential equation in the standard way. We then follow the steps we've come to learn. We identify a v of t by exponentiating an antiderivative of our p of t function. We then plug v of t, p of t, and q of t into our calculating formula to find, ultimately, that u of t is equal to some constant c multiplied by e raised to the power negative kt. To determine the correct value of c, we remind ourselves that u at time 0 equals u0, but also equals c times e raised to the power 0. From this, we conclude that c is equal to u0. The solution to the initial value problem can now be stated as u of t is equal to u0 times e to the negative kt. Although we have a model that relates u and time, we're not done. We've not incorporated all the information we've been given, nor have we actually solved the problem that was posed. We'll deal with these two issues in order. We know that the drug is metabolized at a rate of p times 100% per hour. So let's try first to connect that to the rate constant k. Dividing both sides of our model by u0 gives us an expression for the fraction of the initial amount of drug remaining after t hours. This model can be expressed in a slightly different way using properties of exponents. If the drug is metabolized at a rate of p times 100% per hour, then, after 1 hour, 1 minus p times 100% of the drug has not been metabolized. It follows that u at time t is equal to 1 divided by u0 is equal to 1 minus p. This, in turn, is equal to e raised to the power negative k, and so k must be equal to negative ln of 1 minus p. This observation gives us a way to rewrite our model for the fraction of drug remaining at time t. That fraction can be expressed as 1 minus p to the power t. Let's not forget that we have an actual question to answer. We want to know when the amount of drug has fallen below 1% of the initial dose given. Using our model on the left, we set u of t over u0 equal to 0.01 and solve for t as follows. We conclude that 1% of the original dose remains after ln of 0.01 divided by ln of 1 minus p hours. Of course, beyond this point, the amount is less than 1%. We should give some time to critical evaluation of the model we just built. In particular, we should think carefully about its weaknesses and how these might have affected our predictions. One key assumption we made is that the drug was dissolved in a constant volume. As far as the model was concerned, our patient wasn't taking on any liquids, nor were they eliminating any liquid. By neglecting changes in volume, we might have undermined our other assumptions about the way metabolism works. We might also have neglected loss of drug from the patient's system due to things like urination. These weaknesses or drawbacks might be enough to convince us that we need a more sophisticated approach to modeling. Fortunately, developing your skills in that direction is our next task. To devise more sophisticated models using differential equations, we'll rely on conservation laws. A conservation law is built on the idea that we can represent a system as a compartment that contains some quantity of interest. Inside the system, the quantity might be built, born, or generally produced. Inside the system, the quantity might also be destroyed, killed, or generally consumed. Conservation laws also recognize that the quantity of interest can be gained from sources outside the system and lost from the system to other locations. When using a conservation law to formulate a differential equation model, we focus by convention on the net rate of production within the system and the net rate of loss from the system. Thus, the time rate of change in the quantity of interest is the net production rate inside the system minus the net rate of loss. Let's now use a conservation law to tackle a more complicated problem. Suppose a 100 mg per liter solution of drug is administered continuously with an IV at a rate of 80 milliliters per hour. We'll also suppose that the drug is metabolized at a rate of 75% per hour. Let's try to capture this with a recursive differential equation model. We'll use U of t to denote the amount of drug in milligrams at time t and build a differential equation involving du by dt. Remember, we're using a conservation law, and so we have to think about what's going on inside the system, in other words, inside the patient's body, as well as inputs and outputs to the system. The only thing going on inside the system is metabolism. Mirroring our previous work, we'll model metabolism as negative k times u of t, where k is a constant. The negative sign here reminds us that metabolism effectively consumes the drug inside the patient's body. Following from our previous work, we can see that the rate constant k is equal to negative ln of 1 minus 0.75, or equivalently 2 ln 2. We didn't emphasize this before, but k is measured as a number per hour, and so the product negative k times u of t can be measured as milligrams per hour. Turning our attention to inputs, we know that 100 milligrams per liter of drug is added at a rate of 80 milliliters per hour. So, we can deduce that the drug enters the system at a rate of 8 milligrams per hour. If we assume that there is no net gain in volume inside the system, then we need to account for loss of drug due to excretion. Given that the patient has 5 liters of blood, we can model the concentration of drug as U of t over 5 in milligrams per liter. This solution leaves the system at 80 milliliters per hour to balance inputs from the IV, meaning that 2 over 125 times U of t milligrams of drug per hour is lost from the system. Using conservation laws as a guide, we can now say that du by dt is equal to the net rate of production inside the system, negative 2 ln 2 times u of t, minus the net loss rate, here represented as the losses minus the inputs. It's worth noting that the units associated with each of the terms in this differential equation match. Each term is measured in milligrams per hour. That gives us some confidence that our differential equation model is correct. To recap, we've seen how we can apply linear differential equations to model the behavior of drugs inside the body. We thought carefully about the assumptions that went into our first drug model, which prompted us to up our game and build a new model based on a conservation law. Once you've mastered the ideas introduced in this video, you should be able to apply conservation laws to develop differential equation models from written descriptions of biological problems. You should also be able to both state and critically evaluate the assumptions that go into the application of conservation laws, with an eye to improving the utility of a model. Remember, this video is just the beginning. Make sure to read the course text and complete the assigned exercises. Also, take some time to talk with your classmates. Have fun challenging each other, and this material will be old hat in no time.